So, during this weekend, due to your very interesting and inspiring feedback, I produced a little write-up of the thoughts I presented in this lecture. And you see here 3 authors. One, Elena, is working at the bank in Zurich. Anya is one of my postdocs, and myself. Elena and Anya did not really cooperate in the development of the theory, but we have been doing some empirical work. And due to the discussions with them and also the feedback from data what we received, so a couple of the ideas emerged. So it is fair and right that they are also part of this write-up, even though they did not write a line so far. But it will change.
It's normal.
Yeah. So you see, introduction is nothing. I just want to use this write-up in order to refresh some notation. So you remember the first definition was we have an adapted process taking values in Rn, and we call a family of stochastic processes eta S, having 2 parameters u and t, forward characteristics of the process x, if the conditional Fourier transform of the increments of the process x is given by this sum, which in continuous time would correspond to an integral. So this should also remind you that time is always discrete. Here, s and t are discrete parameters taking values in the natural numbers. U is a continuous parameter. This is the Fourier transform, or the dual parameter.
Okay.
Yeah.
Tell you that, in fact, in probability theory, people usually call it characteristic function, and it's not exactly Fourier transform because it's sort of inverse Fourier transform. You're writing, classical Fourier transform is given by minus ix.
Well,
and this is the difference between analytical approach and probabilistic approach. This is exactly characteristic function, what's called.
Conditional characteristic function.
Yes.
By abuse of notation, I call it Fourier transform.
Yeah.
Since the Fourier, since the transformation u to minus u is also not changing the nature.
I'm thinking not in essence, but
No, I see the point.
Yeah.
So, in order to get eta, if it exists, unique, we should consider or think to have a normalization. At 0, we want to set it 0. This is the first requirement I impose on the process eta. So for u equals 0, we shall always have 0. And then we can uniquely define by complex logarithms the eta. Good, so these are the forward characteristics. Apparently, forward characteristics are related to the notion of characteristics in this discrete time setting. And this would be defined in the following way. You call a stochastic process kappa, depending on x, the process of characteristics, or the process characteristic of x, if this corresponds to the conditional characteristic function of the increment.
This kappa is usually called characteristic exponent.
Yeah, I call it process characteristic.
Okay.
It's characteristic exponent in the case of a Levy process,
Yes,
but
yes,
otherwise
yes.
in the case of a semi-martingale, it's the process characteristic.
Yes.
So there I was thinking of that because it is a process here.
Yeah.
It's not deterministic. And apparently the condition can be rewritten by saying that this stochastic process is a martingale. Yeah? That's the same. And you see also, as always, integrals are replaced by sums. So in the terminology of Charcot and Chayaev, this would correspond to the differentiable predictable characteristic. And this would be the characteristic. Good. Then we have this decomposition property given a martingale epsilon. This is RD valued. An RD valued martingale epsilon. We assume that an increment of the process eta can be written as alpha corresponding to a drift plus sigma epsilon, and you see there's a little error. It should be S here. It should be an S here. So the important aspect is that I decompose the increment into a drift and something which has expectation 0, because epsilon is a martingale. Yeah? So this is the prototype of Meyer decomposition, if you want to see it like that. There is a little subtlety here. Remember, the characteristic is not defined for values s plus 1 greater than t. Yeah, we don't need it for it, and so we did not define it for that. So this means, in fact, here I have s less than t, yeah, for this equation. And for convenience, that my processes are in fact defined always on the same intervals, I introduce alpha tt and sigma tt to be 0. Just that I have always these intervals here. Yeah, this is just for convenience. You could avoid this by talking of predictable processes and so on, but I wanted to stay with adapted. I have one notion of adapted, but I have sometimes shorter intervals of definition, and then I prolong the interval trivially. Good. So this is clear. Now, the important statement comes, which is called proposition 2.6. If we have an adapted stochastic process and a complex valued family of adapted processes, or a family of complex valued adapted processes, I should have written, with this decomposition with respect to a martingale epsilon, then the process eta is a process of forward characteristics if and only if we have this short end condition. So the characteristic of x corresponds to the eta for s equal to t. This is called the left-hand end of this curve eta su, and curve with respect to the third parameter. It's called the short end condition and the drift condition. And the drift condition says that the joint characteristic, when I insert these quantities, gives me the integrated drift with a minus sign plus the characteristic at the short end. The proof was very simple. It was just the statement that if eta is a process of forward characteristics, this equation has to hold true for all s less or equal to t, which means that for s less than t, if I only look at s and s plus 1, I have that this has to have expectation 1. Now we insert our decomposition here. And notice here, the k starts with s plus 1 and goes to t minus 1. Therefore, I leave out one guy, which would correspond to the xs, and this I have to subtract additionally. Yeah, this is this short end condition. Good. I insert my decomposition. I obtain this sum here first, and here with a minus eta, and this second, and I did probably do an error here. Did I? Yeah, there should be pluses here. I'm sorry for that. Should be pluses.
Okay, maybe. Sigma, is it random?
Random, yeah.
But does it depend on, is it anticipated situation?
No, it's adapted. And this should be an S here too.
Mm-hmm. The dependence on K, I just have forgotten what that means.
Sigma I of S UK. This is adapted with respect to this parameter for every U and K.
Oh.
And K is a time parameter. This is
I mean, S is a time parameter as well.
yes, but this is the maturity time. This is running time.
Okay. Yeah.
Maturity time and running time.
Okay.
Yeah? Okay?
Yeah, I see.
But nevertheless,
Yes.
just to make it, let me correct this little error, because then it is better visible what I'm talking about. So, yeah. Huh? Why? It looks, doesn't it look? No. So this is S, therefore I have an epsilon S here.
Yeah.
And here I should have a plus, and here I should have a plus. And to be complete, there was also an epsilon here too much with T. It should be also an epsilon S. And ta-da, that was it. Yeah? So you see, so this, in order to say it probabilistically, this guy always has expectation 0, because this is a martingale increment and this is something which is adapted. And well, when you look at it like that, you see when you calculate the characteristic, the process characteristic of X and of epsilon, if this equals to the process characteristic, then the expectation is 1. And this is just what we write here. The process characteristic at the point U and at the point minus I, such that I obtain a plus here, equals this guy. Yeah? Because the process characteristic is subtracted in this guys. Yeah. That's the drift condition. Yeah? Very clearly expressed. A little subtlety here, I didn't mention it yesterday in order not to mix up the audience completely. Here I sum from S plus 1 to T minus 1, such that I get that guy here. Here I sum from S. Why can I do that? Because if I insert for the K and S, I have only 0. This was just what I used as a normalization before. In fact, this guy is not important in the differential equation, but I can normalize it to 0, and then I can take the sum from S to T minus 1, which allows me to here to simplify the sum a little bit, and later on we will see when we do another coordinate transform, this will be very useful. Otherwise I would need to start with 1 and not with 0, and things would look a little bit more ugly. So I think that's a useful agreement to put it 0 and to start the sum with S. Okay, so that's the statement. Just to mention it, if you write the process xs with respect to the same martingale, yeah, which you can do. Let's assume these are increments of Brownian motions, then you can do that. Then the conditions simplify a little bit, because then it is clear that you can calculate in terms of beta and gamma the characteristic exponent of x, and you can also calculate the characteristic exponent of x and epsilon. This is just taking the definitions of the characteristic exponent. It looks like that, and then the equations can be rephrased in those terms. Yeah. Locally independent meant that x and epsilon move by stochastic forces which are independent. So you can say conditionally on the information fs, nothing about the increment from s to s plus 1 in x if you know all about the increment epsilon. If you have this situation, it sums. We have this summation property, and this brings this property in terms of the drift condition. And this drift condition is well known. You would call it Heath-Jarrell-Morton drift condition in interest rate theory. So this is just this drift condition. It's just the same. For instance, if epsilon is a normal random variable, you have the typical square here minus 1/2, and you get the Heath-Jarrell-Morton condition.
This condition,
Yeah?
Heath-Jarrell-Morton.
Heath-Jarrell-Morton condition?
it appears just in case of local independence.
Yes, because in the case of interest rates, you always have local independence because the x is predictable. We had this yesterday. X is an integral of the short rate, and therefore it is always independent of the driving forces, because predictable processes are always locally independent of martingales. Yeah.
So this is just particular case.
This is a particular case, which I think is the first insight I brought into this whole theory, that if you write it up in proper terms, everything can be seen from the same angle. Yeah. It is not a theory of option price models, it is a theory of term structure models, and all those drift conditions which we obtain there are in fact deductions from the drift condition I had before. Okay, so this is what I tried to mention in this little application section. If we have a bank account process which is e to the power some integral of short rate, yeah, for some short rate process, then we define x as to be this short rate, this integrated short rate process. This is predictable by its very nature of definition, and therefore when we consider the forward characteristics of that process, the equation satisfied by the forward characteristics is particularly simple, and it is the Heath-Jarrell-Morton equation, since this and this, they are conditionally independent. Yeah? If we have the logarithm of a martingale, so we think now of a stock price process S in the martingale measure, so it is a martingale. Then x is the logarithm of a martingale. We assume a little bit more exponential moment out of convenience in order to be able to define up to the boundary points the eta. And then we have, I write again the definition of the forward characteristic, and the martingality condition just translates into eta evaluated at the point minus I. If I put a minus I here, I have e to the power x should be 0, because then the right hand side should only be e to the power xs, because e to the power xt is a martingale. Just this statement. And there's also a little error here. Let me correct it immediately. It should be IU here. Yeah. And you can also look at credit risk theory. I like to look at credit risk theory from a point of view which is like foreign exchange models. So you have something which is a discrete, risk-free bank account process, and you have an instantaneous recovery, which you could also consider as an exchange rate to another currency. And the defaultable bond price is then nothing else than go to the other currency in the future, exchange, and discount this value and upcount it to the value in time fs, take the conditional expectation and change it back into the other currency, then you obtain the value of the bond in the other currency. And if you consider the change of value as an artificial introduction, this corresponds to the instantaneous recovery of the bond. Yeah. So this is an idea going back to Jarrow and Turnbull, that one can see defaultable bonds as bonds in another currency. Yeah. Good. I have a general process here. So I would like to have this as a bank account process, so this is predictable. And the x2 is something general. Yeah. So for instance, imagine this is euro-dollar. Then this is the logarithm of the exchange rate between euros and dollars. And this would be nothing else than the definition of the price of the dollar bond. Yeah. And if you consider the exchange rate not as an exchange rate between two different currencies, but an exchange rate which exchanges a bond written on a, let's say, AAA company into a bond written on a CCC company with the same maturity time, then you can look at it like that. So you see, this is also, can be seen from that point of view, and you get the condition. I mean, there have been many papers where those conditions have all been calculated. I like that point of view because it unifies all those considerations. Affine processes. This was the last example I had yesterday. What is an affine process? An affine process is defined on a closed convex domain, being a Markov process there, and the conditional characteristic functions are of that form. Yeah. Phi and psi being complex valued and being defined on the union of such sets, and these are the sets of dual vectors. I don't call them Fourier vectors now. Dual vectors, such that this the Fourier basis is bounded on the set D, on the domain. There's always a little bit of a mess here. What is the mess? The mess is that some people, including myself here in the talk, like to write an I here. Whereas in the definition of affine processes, usually this is not done. So this is defined like a moment generating function. Yeah. But the moment generating function, if you evaluate it at the purely imaginary subvector spaces, the Fourier transform. And there is a problem with plus or minus. So if you, out of some reason, like the minus here and make a Laplace transform, what some people do, then you have the problem that the set U is not invariant by applying a minus, because it is like a Laplace transform. The function e to the power minus lambda x is on the non-negative numbers bounded for lambda greater or equal than 0. But if you replace lambda by minus lambda, it is not bounded. So one has to be careful at this point. And I mention it because sometimes formulas, and the formulas here are usually complicated. People make the error just at the beginning. Yeah. Which affine processes do we know? Levy processes have a conditional characteristic function of the type. Ornstein-Uhlenbeck processes have a characteristic function of the type. But it would not be worth introducing for those two types of processes this setting. The most important example, in my opinion, are squared Bessel processes. So here we have also a conditional characteristic function of the type, and this makes the class interesting. And then you have concatenations of those types of processes. So for instance, the Heston model is also of that type. Heston model is an affine model. And as we already said yesterday, a good part of the models used in mathematical finance are affine. So the Heston model, the Bates model, the Merton model, Black-Scholes, exponential Levy models, they all have the property that when you do a deterministic transformation of the price process, you end up with an affine model. Also, to answer one question which was mentioned yesterday, from a point of view of stochastic differential equations, these are not necessarily stochastic differential equations with constant coefficients. So the Heston model does not have constant coefficients. It has these typical square root structures. Good.
They have to be affine functions.
Right.
Those coefficients.
Affine functions. Yeah.
And you got drift and square of variance.
Of the volatilities, yeah. Or when you have jumps,
yes, you can put
the Levy measure should have an affine structure. So, since the conditional characteristic function has this nice form, we are able to say what are the process characteristics. The process characteristics at U correspond to this form above at IU. Yeah? And I write it down. And then you can take first differences in order to evaluate the eta. And you see just this type of structure where the F and the R are the operations expressing the first differences. So when you take the first differences of the phi's with respect to t and the first differences of the psi's, this is given by a function f and r, which in fact can be determined at the beginning, so at t equal to s, and this is due to the structure that phi and psi satisfy a semigroup property. And this semigroup property means that when you know it here, you can, by iteration, calculate it everywhere.
Every time homogeneous affine process, you can do
This, right. For every time here, in this case, even inhomogeneous affine process, I can do precisely this. I know that there are functions phi and psi from those functions phi and psi, I can define myself an f and an r, and the phi and psi satisfies these difference equations. And the other way around, if I give you f and r satisfying very minor properties. So in fact, f and r basically have to be logarithms of characteristic functions. If I have such a property, then I can define an affine process with that. So it's a very simple characterization theorem. And it follows out of the
So you from understanding you can construct something.
Yeah, sure. It's not a strange question. It is like that when you take an Ornstein-Uhlenbeck process, a Levy process, whatever, you can do such a discrete affine process by evaluating it discretely. And you know the Ornstein-Uhlenbeck, what is the psi in the case of the Ornstein-Uhlenbeck process? If you take an Ornstein-Uhlenbeck process, let's say a real valued one, then the psi of u and t would be e to the power a t u. Yeah? The r in this discrete setting is e to the power a at the first increment, u minus u. Yeah? And further. Yeah? And then you see immediately why the equation holds. Yeah? But more fascinating is the example of the squared Bessel process. Because there, the psi has such a typical let me put it like that, has such a typical Möbius transform structure, and then it's a more interesting example that comes out.
Actually, I tried recently to calculate full property.
Yeah, it's true. This Möbius, yeah. But it, it's a solution of a Riccati equation. And this is the discretization of the Riccati equations. So this follows from the Tower property. Yeah. Now something new. So that's now the interesting part, which is new. And maybe I zoom in a little bit. Yeah. This so-called Hull-White extension. So we consider a time homogeneous affine process. Yeah? And we consider a set of forward characteristics. So they should lie in gamma d, and those mu's which appear here are logarithms of increments of stochastic processes. And the d always says that the gamma is a set of logarithms of characteristic functions of stochastic processes, and the increments are logarithms of increments of stochastic processes. And the increments, the d means that when I add such an increment to a point in d, I always stay inside. So imagine real, non-negative real line. What is an increment which leaves the non-negative real line invariant? So this is a process which only moves in the positive direction, so a subordinator. So the increment is always non-negative, and if I add the increment to then it's the case. So in other words, Ix is a set of initial configurations which lie above, in the sense of logarithms of a Fourier transform, in the sense that the logarithm of a Fourier transform is added. They lie above a given affine process. So this would be from the affine process at time t, the characteristic function, and then I have something which is additionally added. And the something which is additionally added is in fact of this particular form, y. This is explained by the theorem. The theorem tells if I have a time homogeneous affine process with characterizing functions phi and psi, then for every initial value x and every eta which I find in this set Ix, there is a unique stochastic process starting at the little x, which has a new characterizing function phi tilde and the same psi, such that this equation holds. Yeah, and error, this should be a tilde here. Let me correct that quickly. So this is a phenomenon which in finance is called Hall-White extension. And imagine x is the integral. So when we take an example from interest rate theory, let's say x equals the integral of Rs ds, and the Rs in interest rate theory is very often an Ornstein-Uhlenbeck process. Yeah. So then R, t, and xt together are affine. And you have a phi and a psi for that. Yeah? And the statement of the Hall-White extension is, if I consider the bond prices in this setting. So the bond prices are like that. And I do that at time 0. Then having the structure fixed with parameters which are there, also this curve is fixed. It only depends on the parameters. If you come with an arbitrary curve from the market, you will probably not be able to explain it by this 1, 2, 3 parameter curve. So it might be that the curve simply does not look like the curve you have here. Hall-White extension is the question, or the answer to the question, how do I have to change the Ornstein-Uhlenbeck process such that I can fit any curve here? Any under quotation marks. More, let's say. And the idea of Hall-White was simply to say, when I have the Ornstein-Uhlenbeck process, I have the constant drift part, which is the B. I have some A, which is the mean reversion rate, and I have some Brownian part. The Hall-White statement is, if I make this guy time dependent, then I can fit any initial configuration. Here's a similar situation. Maybe, put, in my opinion, into a more general and also correct context. I start with a configuration which does not come from an affine process, or not from the affine process I have, and I ask myself, is it possible to change the affine process by passing from a phi to a phi tilde such that the initial configuration is replicated by this? And the answer will be very simple. I put the setting just like that.
Excuse me, in which measure you compute this expectation? You have fixed it.
This is always the martingale measure. Yeah, it's a fixed measure. Yeah. This is an interesting question. Hull-White extensions and change of measure. Yeah. You remember in this interest rate setting, every measure was a martingale measure from the original point of view. So you could say you take a measure such that you have this nicely here. You can interpret it like that, that you generate this value here. But nevertheless, with respect to the martingale measure, the UU process then has a particular structure. Yeah? No, this is general for affine processes. Because for an affine process, it is always like that the B and the sigma, everything where you do not have a multiplication with the state variable, this goes into the F. And everything where you have a multiplication with a state variable, this goes into the R. And the F corresponds to the phi, and the R corresponds to the psi. So if I do the Hull-White extension, I change the F. And if I change the F, I change the phi. Therefore, here only the phi is changed and the psi not. But this is completely general. You could do the same thing with Cox-Singer-Ross or higher dimensional models.
So by this way, you can change a little bit this right-hand side.
Right. This is just what I want to do. I just say, if I have a phi here, the right-hand side is fixed. But everything which somehow lies above the phi, I can also replicate by an affine process. But this affine process has then a time inhomogeneous structure. It's called Hull-White extension. No. But the proof is very simple. So what do I want? I know I have an eta, which is this initial configuration. I don't know if there's an affine process giving me this initial configuration. But I know that the eta looks like this, from the affine process plus this something. Yeah? This is the definition. This is how I define the eta. Then I define a new stochastic process through the following difference equation. I say the new stochastic process satisfies x tilde t plus 1 minus x tilde is take the affine process from before, start it at the process x tilde, which I have constructed at this point in time, and add the increment which corresponds to the mu, because mu is a logarithm of increments of a stochastic process, such that this is independent of that. I make maybe an extension of my probability space, and then I have this structure. When I do that, which is easy to write down, I obtain, due to the fact that here the characteristic function of those increments is the mu, and yeah, simply by looking at the, let's say, conditional expectations and conditional characteristic functions, when I calculate the characteristic function of x tilde t, I can do it like that. I write x tilde t minus x tilde t minus 1 plus x tilde t minus 1, so I introduce this 0. Then I know I can introduce a conditional expectation here by the Tower property. this part here goes out, put it here, and this part here can be written as the conditional expectation of the x process starting at x tilde t minus 1, this was just a definition, minus x tilde t minus 1. Plus the mu, this is the conditional expectation of the increment. And having that statement said, I end up with what I just wanted to do by iterating it. So the equation which I have here satisfied is just what I obtain when I iterate the previous conditional expectations. So when I have an eta which is of that form, I can easily generate an affine process which does my job. Yeah? I can easily, yeah? This, yeah, but it's again, you have to somehow write it, it's a little bit more delicate to write it down. A little bit more delicate. Let me just think about one aspect.
We can make a break. I can move to take photos. 5 minutes break.
The last line.
No, it's okay. It's just
Should be one more bracket. Exponent.
There should be one more bracket. Yeah, yeah. No. I was just thinking about this minus u here. Yeah, but this is just what it should be. Yeah. Yeah. So this is the construction of this Hall-White extension. Maybe it's a good point to make a break. So it is a statement that when you have an affine process which produces this type of initial configuration, you can also produce more general types of initial configurations by constructing a new process in the how I stated it. And this will have a funny meaning. We will see that in 5 minutes. So we make a break. And let me include the brackets here. So to put it again, if I may restart, the question is if we have an affine process, time homogeneous, and if we have a configuration which is different from the initial configuration of the affine process. What do I mean with configuration? The eta zero of the affine process. So the forward characteristic at time 0. This is nothing else than the characteristic function of the marginal distributions. When this is different, you would first say, well, it might be difficult to construct a process which has different marginal distributions. But in case of affine processes, if the difference between the two guys is of such a type, you can construct an affine process which does the job. This is nothing else than the generalization of the idea of Hall-White extension. And it is very natural. You simply say the new process, which appears to be also of an affine time inhomogeneous type, the increment of the new process is the increment of the old process started at the value of the new process plus the new increment. It's very simple. Huh? Let me put that bracket here. I like when things are correct. Zack. And this equation is then nothing else. Introduce the 0. Here you have this increment which you defined before by the difference equation. This is ft minus 1 measurable. Then you calculate the characteristic function of the increment conditional on ft minus 1. This is the conditional characteristic function of the affine process x, which I had at the beginning, started at x tilde, plus the conditional characteristic function of the increment nu, which is independent of ft minus 1. So this gives me that quantity here, plus what remains from here. So there, one guy cancels out. This gives me the f. Yeah. This would give me the r, but I'm not considering that. I'm just doing this conditional trick again. I go to ft minus 2 until I'm an fs, and then I do nothing else than solving the equation and obtain this quantity here. The application of that you will see in a second. So far it is only the somehow surprising fact that I give you an affine process and I give you a family of marginal distributions which are different from the affine processes, marginal distributions, and I still say if this difference is of a certain type, I can construct a process. Now we come to the stochastic difference equation for forward characteristics, and this particular Hall-White extension will play a role there, an important role. So I want to come to a setting such that I can talk about Markov processes. My Markov processes are now Markov processes of forward characteristics. The state space is denoted by the state space of the process x times a theta d. And in fact, we are not taking theta d right away. We take a theta n and Rn instead of d, and we say then we write maybe our difference equation only on a subset. And finally, we also say theta n is not nice enough. This will be logarithms of characteristic functions. We rather think of a Hilbert space of complex valued functions being defined on the appropriate variables. And then we ask ourselves afterwards, a posteriori, if the solution of the difference equation stays in the set theta n where it has to stay in order to be a forward characteristic. What is a forward characteristic? A forward characteristic is a function in two variables, u and k, such that if I do that sum, this is a logarithm of a characteristic function of a stochastic process. That's all. That's a forward characteristic. Yeah. So it's clear now. The Hilbert space which we are considering as a first Hilbert space, these are, yeah, it's not, you see that it comes from continuous time. No, at this point it's correct. We have a Hilbert space of continuous complex valued functions on Rn. This does not mean that I make all continuous functions a Hilbert space, but I have a Hilbert space which has an embedding, continuous embedding into continuous functions. Yeah. What is my forward configuration Hilbert space? This is a space of functions eta indexed by natural numbers taking values in G. And I want that this is lying in L2 with some weight. Yeah, there should be an n here, sorry. Some weight. So. Such that we have a continuous embedding into that space. So every element of H can be understood as a map from the natural numbers to G. G's are maps from Rn to C, so we can in fact understand it as a map from this variable and this variable to C. And I want that this embedding is serious. I have that. Well?
What do you mean by continuous embedding? You have small two objects and...
if I have convergence here, it converges here. If I have convergence here, it converges here. Yeah? In this topology L infinity log. Yeah.
Yeah.
And log is meant with respect to both variables. Yeah. So I just want to say it easily. If I have a sequence of functions, let's say eta n from n times Rn to C, and this converges in my Hilbert.
N will map from Rn to C, not from N. Yeah? This index you have chosen.
This I did not understand what you said.
I said that eta maps from N to, but eta N.
Sorry, the n is not that I insert here an n.
Yeah.
The n is a sequence index. So eta, every eta is a map from n times Rn to C. I use something which I call exponential law. So when I have a map to a space of maps, I can also write it as a map on the product. So eta for me is always, it was always in this lecture, a map on the product. Time times Fourier variable, u and k. Yeah? And now I take a sequence of those guys. If this sequence converges to some eta in the Hilbert space H, it follows that locally in that space it converges. This means take a compact set here and take a compact set here, which means a finite set, then I have convergence. It's a very natural way of doing it. Second statement, more important, the shift semigroup acts as a strongly continuous semigroup of linear operators on H. I write that in order to have a meaning in continuous time. In discrete time, this is not a condition. This is always true. Yeah? In continuous time, this would be a condition. And the third guy is somehow the probabilistic guy. It should not be any Hilbert space. It should be a Hilbert space where finite activity Levi-Khinchin type guys, at least those guys lie there. So this means the increments which I can consider in order to build my general processes are of the type time-dependent Levi increments. So you have something drifting, some diffusion, and some jump. You look horrified.
No.
No, it's okay. So this is just a statement that the eta has representatives of this type.
And you need the finiteness of Levi measure.
Here I take them. Here I take finite activity.
Yes.
But I just want to say here the following thing. I mean, I say that those guys lie inside. H is a Hilbert space, so I will also have sequences of those guys. And if the norm of the Hilbert space or the scalar product is appropriate, you will get infinite activity. Even maybe infinite total variation, if you want. It's just to make a statement what we should have inside for sure. Now comes one decisive aspect. In order to write a good stochastic difference equation, I need to guarantee that I have a state space where my process stays. And the state space will be this Hilbert space H. But in order to guarantee this from our setting, you remember the forward characteristics, they were only defined for times which are greater or equal than S here. Now I make a time transformation. I say I write everything with the variable x, and x is the difference between t and s. Now I have two non-negative variables. One is the x and one is the s. Before I had two variables. One was the t and one was the s, and t was greater or equal than s. This is easier now. But nothing is for free in life, in particular if you have a good effect of it. The problem which comes out is that the equation looks more complicated. Before we had alpha, sigma, that was it. Now we have this additional shift term. Why is that? Let me write that on the board.
Somehow describe all possible forward characteristics.
Yeah, we have now in this in the last lectures, we have now a space of possible forward characteristics, or we have a space which contains forward characteristics. It's somehow difficult to say how the space of forward characteristics solely looks like. But we have a space H. An element of this H is a typical guy N Rn to C. So at least formally this qualifies as a forward characteristic. Such a space we have. And what are when we think of forward characteristics, what do we think of? A forward characteristic should be something like that. S plus 1 minus xs EU scalar product Fs evaluated at omega. This should be the forward characteristic of S US evaluated at omega. So you see, a typical forward characteristic is the logarithm of a characteristic function. And what are logarithms of characteristic functions which we like? For instance, all the Levi-Khinchin guys. These are typical logarithms of characteristic functions. The ones we like most, or some people like most. They are not necessarily of that type, but I just want to say they lie for sure inside. Others can lie inside, but these are for sure inside. Because I wrote a Hilbert space and I want to have a Hilbert space which at least contains the Gaussians. Yeah? So it was that statement. And now I say forward characteristics are always measured somehow relative to the point in time where I am. And now I say, in order to have a nice state space, I don't want to always speak about processes which look like that. I would rather like to speak about processes like that. Because then I have the process variable and the second variable independent of each other. And the trick to do that is to introduce time to majority and to say that eta s u x equals to eta s u t plus x. No, s plus x. Yeah?
The distinction is always connected with infinite divisibility. need, we just need...
We don't have it, but we could have it. We could have it, but we don't. Not necessarily. To be also precise, if you do it in continuous time, eta SS will be infinitely divisible. One can prove that. Even though it's quite a, in my opinion, yeah, it's a proof which is of the same structure as when you have predictable characteristics of a semi-martingale, that they are infinitely divisible in that sense. Okay. Now we write our difference equation. The difference equation.
You were saying about infinitely divisibility of eta or of the process.
Yeah, I used it synonymously. So the process X has an infinitely divisible distribution, then I call eta of a Levi-Khinchine type. Let's write what is meant with this difference equation. Eta plus 1 at the point u at the point x minus eta, no, theta, at the point u at the point x equals to S1, this is the shift by 1 in the second variable, u x plus 1 minus theta t u x. And then comes the rest. Yeah? And you see that you have a cancellation of that guy with that guy. And what remains is this minus this. Yeah? Which is nothing else than eta at time t plus 1 u x plus t plus 1 minus eta at time t u x plus t plus 1. And the important thing is that you here have the same variable, because for this equation we know the drift condition. Therefore, when I write that here, I need to correct it by that in order to obtain the same equation. It's just when I do the coordinate transform, I get this additional term. Otherwise, I compare apple with pears. Yeah. Everything else is the same, and I use even the same letters, alpha and sigma, which I had in the decomposition before. This is called the term structure equation for forward characteristics with vector fields alpha and sigma, an initial term structure eta, theta 0, and an initial value x0. S1 is the shift. We have the consistency condition. So this means the short end of theta, the most left endpoint of this curve, should be equal to the characteristic exponent of the process x, which was calculated by a formula before. The characteristic exponent of the process x, and then I have the drift condition, the integrated drift plus the characteristic exponent equals to that guy. Let's look backwards. What does this mean for that equation? Maybe I do something which might help at this point. Let me use my most beloved tool here. So this is the geometry of polar surface models. And my most beloved tool is that guy. Yeah. So this is the equation for x. Yeah? This is the equation for x with respect to the semi-martingale epsilon. Below I have the equation for theta with respect to epsilon. In the Musiela parametrization, this means I have this additional term here. I explained that before. Now you would say, why do I only speak of alpha and sigma here? Why do I not speak of beta and gamma? And second, alpha and sigma are written as maps from x and theta, but beta and gamma are not specified like that. The idea is that finally we would like to have a stochastic, lower. Is it okay like that? Lower? Okay. I would like to have a stochastic difference equation for theta and construct out of that the x. Because the idea in modeling is always that you take the observed data, assume a certain model for the observed object, and then you construct out of that a model which cooperates with the data in the best possible sense. So the model to be constructed is the x, and the observed guys are in fact here. Yeah? How does this reflect to the equation? You would say when you see that equation there's something unspecified. I have initial values, I have the alpha and the sigma, but how do I get the beta and the gamma? The answer is very simple. When you look at point number 2 here, you see here an equation that the short end of the curve theta specifies a function of gamma and beta. In other words, the characteristic exponent, so this is the logarithm of the characteristic function of the next increment of the process S, is given by the short end of the curve. This is what we always said. When you take the curve of the etas at the left-hand side, you see just the characteristic exponent of the next increment.
Okay, once I would like to begin. Why eta was bad for you? Why you needed eta?
Because I want to write an equation which has a state space. State space comes from the fact that I decouple the variables s and t. Yeah, otherwise I don't have them decoupled. Yeah. So look at that equation before, and let's look at the equation at time s equal to 0. When I have time s equal to 0, I have an initial theta 0. Out of the theta 0 at the value time 0, I calculate gamma and beta at time 0. Then I make the first step in my equation. This means, in terms of simulation, you simulate one step, you calculate theta 1. By doing that, everything is now specified. And you calculate x1. Yeah? Then you have to go again to this condition here and say, now I have my theta 1, and I can calculate my gamma 1 and my beta 1 in order to make the next step in x. And for the next step in theta, I have already everything. So there everything is specified. So this means, the insight is that this somehow funny looking difference equation is in fact well specified because the consistency condition tells that the beta and gamma can be online calculated out of the left endpoint of theta, of the short end of theta. Also, I want to emphasize here, if we were doing that in continuous time, you would not hear that here anymore because you cannot present it in a week. it is much more technically challenging to write that down. So for instance, in the paper of Jan Carlsen and Paul Grüner, this point of view is not mentioned because technically it would be very unfriendly to be expressed. Yeah?
You just calculate them, or you can say some theoretical facts about
Yeah, let's put it like that. If the short end of this curve is of the type, let's say, is of Levi-Khinchin type, then you can say what the beta and the gamma are conditional on the state of the word. Yeah? It's an inversion of this function applied to that. And we know in the theory of Levi processes, when you have that this is of Levi-Khinchin type and that this is of Levi-Khinchin type, you can identify drift with drift, volar with volar, and the jumps separately. It's not a nice identification, so it is not easy to split it, but it is a unique decomposition. Yeah. Good. And the second guy is of after you have specified beta and gamma, you have to check that the alpha satisfies the correct relationship, and then you can write down that. Yeah. So you see, if you were solving this equation, this difference equation, by an Euler scheme, as you would do it when you see it like that, you have to do a couple of things. First, you have to initially specify x0 and eta 0. Then you have to take the eta 0, evaluate it at time 0, calculate the beta 0 and the gamma 0. Then you have to take the sigma and check whether the alpha and the sigma at time 0 satisfy this condition. And then you can do the first step. Then you obtain a theta 1 and an x1. And then you do that again. This is complicated, even in discrete time. And you can imagine this is the very reason why every paper written on term structure modeling in continuous time is tremendously complicated. Because you have just this somehow. The equation is always speaking to itself. At every infinitesimal point, you cannot somehow ad hoc write the equation down and say, this is how it looks. You have at every point always to update and to include the information. Because we are constructing finally a stochastic process which has a certain property, namely that its marginal distributions are given from the beginning. And I have a certain dynamics, sigma is also given, on the forward characteristics. So this is a very non-linear constraint. You say you have a dynamics on the forward characteristics and the initial marginal distributions are given. So, no, the marginal distributions are given, ab initio. So this non-linear constraint is satisfied here, but it can't be easy. But you see, in the discrete setting, at least, you can close the loop. You do not need a somehow fixed point theorem or something like that. You have a way how to make it forward. Yeah. But this has to do with the discrete world here. Okay. Now the statement is very clear. The theorem which follows afterwards is if we have a term structure equation for forward characteristics with some initial value, and we assume that beta and gamma are uniquely specified through the equation, then the process X together with eta, defined in that way, is a process together with its forward characteristics. Yeah? If this forward-looking equation can be solved, then everything is done. The point lies here in uniquely specifying beta and gamma. It might well be that the equation number 2, the equation on the theta, leads out of the state space, and then you cannot specify beta and gamma. Yeah. And the proof is certainly a consequence of the condition proposition at the beginning, because these are just the same conditions. So you see, it's a funny equation, still looking simple, still being, one is able to simulate it, but intertwined. It's an intertwined thing. It's not absolutely easy to understand object.
So is this somehow connected with this that we had yesterday?
The drift condition. Yeah, it's the same. It's just the same. So the alpha satisfies the drift condition which we had yesterday, and then the process theta together with the x, this is a process of forward characteristics together with its mother process, say it like that. Yeah.
And the conditions that we have, this is condition for x epsilon, x epsilon.
Say it again. You were referring to, yeah, this is a condition which holds for x, yeah, and for s. For every s and for every x, and certainly for every point in my state space. But when you solve the equation, you can write it down online. It is not something which you need to calculate before. So the question which remains is the following. Can we write down solutions of this difference equation which are not too simple and still solve that equation? That's the question. And it's a non-trivial question in the sense we see that the equation is certainly not easy. And I mean with a solution that I do not only have a solution for one initial value. So certainly every Markov process or every semi-martingale in that setting provides me with one solution of that equation. But this is not what I actually mean, because here I have a somehow Markovian structure. If I take any process x, this will not be a Markovian structure anymore. This will be something which is then any solution. So what are interesting solutions coming from a Markovian structure for certain vector fields sigma and alpha? Alpha is determined by the sigma, so in fact the only thing to say is for which sigmas can we write down solutions of those equations easily? And the answer is for all sigmas which belong to affine processes. What is a sigma belonging to an affine process? As Jana already said, these are guys where you have such a structure that squares of certain coordinates which appear in the sigma are affine in the underlying. How do we see that here? I mean, this is it's an abstract setting, so we have to find out a way how to express this statement easily. And the most interesting way, in my opinion, is the following. We say, yeah, maybe I make a stop here simply. Is there a shutter? No. It's an international one. we stop it. Huh?
If it's international language, you know better.
No, I'm not so sure about that. Yeah. For better times, duck. Please wait for better times. But the times are already good, is the Markovian answer. So the statement is we have this stochastic difference equation with its complicated structure, and we would like to say what are nice solutions of that equation. And I write it now again a little bit more abstract. I simply say I have an equation of the type theta t plus 1 minus theta t equals to an operator plus something here plus something here. And I ask myself, because everything else is a function of it. No. I ask myself, under which conditions do I have the structure that I find a finite dimensional submanifold of my state Hilbert space such that the equation leaves this submanifold invariant for theta 0 in the submanifold. I have all solutions lie in the submanifold almost surely. When do I have that? Again, in continuous time, this would be a quite delicate question. There are a couple of things to be observed. In discrete time, this is a question which you can solve under some assumptions quite directly. If you assume that the increments of the epsilon t are independent of ft, and that the support of the increments is always Rd, then you can immediately follow out of the fact that at the beginning you start with theta 0 and then you have the theta 1, then you know for all theta in the manifold and for all lambda in Rd, you have immediately theta plus a theta plus alpha theta plus I goes from 1 to d, sigma I theta lambda I. This has to lie in the submanifold. Out of the simple reason that for every realization of my increment delta epsilon, this lies in the manifold. The support of this is Rd, so this always lies inside. So this means my submanifold contains an affine subspace. Yeah? And out of that, you see that the structure of affine processes where the theta is of the form f of psi, to be precise, theta ux, psi t ux, plus r psi ux with the affine process. I call it now Z. This is just of this affine form. So you have some coordinate process Z, and you have something which is affine in my space. I have some guy here, plus a direction in my Hilbert space applied to this vector. So these are examples of submanifolds where you have a affine subspace.
In zero, it said something about increments. Yes? And
Yeah.
Space of increments. And here you write.
Here I make a conclusion.
Mm-hmm.
Here I just make a statement. If I have an affine process, it is always of the form that it lies in an affine subset of my Hilbert space. Affine in the sense, what is the manifold? The manifold is in that sense at time t plus r psi ux z. So it's a manifold where you have one guy plus z times a couple of guys. It is affine in the variable z.
Mm-hmm.
And I just say that this conclusion here, if I have independent increments, is satisfied in particular if I have affine processes. Just to make clear why I consider that interesting. So this conclusion here is satisfied here.
Okay.
The manifold which I have here is of this type.
Okay.
I want to ask, I somehow was interested in the question, is this a very, very special case, or do we have in the general case, if we have any manifold, also this structure? And the answer is, even in the general case, we always have this affine structure. So now the final question is, do the affine processes correspond to some difference equation of that type? Does that correspond to such an equation? And without keeping you too long here, the answer is yes, but it is a little bit, well, how shall I say? It is to be written down complicated, but to be formulated easily. So the R, this is a fixed direction in my Hilbert space, together with the characteristics of the process Z as an affine process constitute some of those vector fields sigma. And I have to be careful now. I have the characteristics which correspond to the F and the one which correspond to the R. Everything which is related to the R is what I put into the vector field sigma, and everything which is related to the F I put off first, because it will go into the alpha. And somehow, with this type of consideration, we will be able to write down vector field sigmas which correspond to an affine process, such that the difference equation has solutions not only for the starting values which correspond to the marginal distributions of the affine process, but for everything which lies in my Ix. And there you see this foliation. So the funny thing is that this complicated looking equation not only has affine subspaces as finite dimensional realizations, additionally the affine processes just come or can be expressed in such an equation, which is a little bit interesting, because a complicated equation has now a couple of interesting solutions. And therefore the solution theory I mentioned yesterday of that equation is to say, in each step I use that I have an affine structure which could realize this, and I simply concatenate on one step, one affine process with another affine process with another affine process in order to obtain a complicated solution which I'm interested in. What does this mean in concrete terms? If you take the Heston model, for instance, and if you have a volatility surface, what do we do? What do Anja Richter and Elena, what are we doing? We take a volatility surface, we fit the Heston model to the volatility surface. What happens? The Heston model does not fully explain the volatility surface. There is something which remains left. So the Heston model is not good enough in order to explain the volatility surface. If the Heston model always were good enough, yeah? Yeah. If the Heston model were good enough in order to explain the volatility surface, I don't need to do this exercise. But it is not good enough. So I have to add something to the Heston model in order to explain the volatility surface. This is my F tilde. I have to add an additional, in our case, it's a generalized hyperbolic process in order to explain the fine structure of what is missing. Yeah? This I do with today's volatility surface. I have a whole time series of volatility surface. I have it yesterday, I will have it tomorrow. I do that every day. What I observe when I do that is the recalibration issue, that today my Heston parameters are a certain vector, tomorrow it's another vector. Not wildly different, but a little bit different. Usually people say this recalibration problem is killing you, in the sense when you have that issue, you can throw away your model because you have every day somehow a different model. And the answer I give with that theoretical insight here, it's that this conclusion is wrong. In fact, you can use this. This is nothing else than saying that even though the Heston models change, and this change is somehow done without constraints, so you don't know what will be the value of the Heston vector tomorrow, and you have some stochastics for that, you can concatenate those different models in the sense I described here before. So, statement is from a stochastic point of view, there is still a stochastic process which has the property that it fits to these different Heston vectors and to these different generalized hyperbolic vectors every day, and which has the marginal distributions of Heston. Such a process exists. This is the stochastic statement, and the mass finance statement is recalibration can be done reasonably, but you have to see it from that infinite dimensional point of view. No. That's the conclusion. I stop here.